This video is the first in two installments on Kirchhoff's rules. Kirchhoff's rules are just consequences of conservation of energy and conservation of charge. And so we're going to apply them in some simple circuits to start, and then the second installment will be a practice of a kind of a more complex circuit. The second thing that you'll need to know is that there'll be several times throughout this video that I'm going to pause. And I'm going to ask you to do something. I'd like you to pause and do that with me or on your own, I guess. And then I will come back on and I will have that text written on the board. I'm just trying to make sure that this is as efficient as possible with you not having to watch me write out a bunch of stuff, because that's kind of silly and a waste of your time. All right, so let's start with Kirchhoff's loop rule. And it is an application of conservation of energy. So essentially what it says is the sum of the differences in potential around a closed loop is equal to 0. We talked about this when we talked about terminal voltage, right? You can think of it as a hill. If you go for that walk, starting from home, go around the block, you're at different elevations, but you end up at the same height or the same potential. The same is true around the loop of a circuit. So what it looks like in practice, what it looks like is you need to start at any point in a circuit and then mark that. And then you're going to write an equation for the potential differences while you make a complete loop around the circuit. So again, think of the hill analogy. Are you going uphill or downhill? The signs here are what's tricky, not actually identifying those different potentials, but identifying their signs, whether those are positive or negative. So when you get to a resistor, the potential difference across a resistor is negative if you are moving in the direction of the current. That means you're going to go downhill or to a lower potential. If the potential is positive, if you're going in the opposite direction of the current, meaning you're traveling around the loop uphill. It does not matter which direction you transverse the loop. You just need to be consistent and continue through the same direction and pay attention to your signs. So what we're going to do now is we're going to practice one of these. So here's a simple circuit, and we are going to start at point A. So point A is right here. And if you notice, that's connected to the 0 potential, or that negative terminal of our EMF, or our ideal battery in this case. And so that's going to be what we would consider our 0. The other thing that we have to keep in mind is that these are differences in potential. We're not actually looking at the potential itself. We want to know what that difference in potential is. So at this time, I'm going to ask you to pause the video. I'm going to ask you to start at point A, and let's all go around the loop with the direction of the current. So we're going to transverse this loop in a clockwise direction, and I'd like you to try to write an equation that represents the potential difference across each of the components, the EMF, the resistor 1, resistor 2, and resistor 3 around the entire loop. So pause the video now, give that a shot, and I'll come back in just a moment to help you with that. Okay, so here's what I have. As I started at A and I transversed around my loop, the first difference in potential that I encountered was my EMF. And since we're going from the negative, or the lowest part of that potential, up to the positive terminal, that's going to be our high part, that's a positive. And I didn't write the positive in front of that EMF symbol, just simply because that is assumed, right? So that's positive. So then as we go around our circuit, we encounter this first resistor. And since we are moving in the direction of the current, that's going to be downhill. Sorry about that. That's going to end up being downhill. And when that goes downhill, we have a negative sign in front of that V1. And then again, we continue to transverse that loop. And now we come to R2 right here, and our potential across R2 is going to be negative again, because again, we're going along with the current. And then we continue our loop around, starting at our R2, going through our R3. We have a potential difference across R3. Again, it's like a step down, and so then we have that negative sign. That entire loop, since we are now back to our starting point, right? So we got to go all the way around the loop back to the starting point. Those differences in potential, or again, those differences in heights, will be equal to 0. Now, this is important. We can actually rewrite this in terms of currents and resistances. So again, I'm going to ask you to pause the video, and I'd like you to look very carefully at V1, 2, and 3, and I want you to rewrite that in terms of current and resistance. So I'll pause the video again, and please do that. I now have part of this equation written out, and I want you to notice I made a couple of changes. Instead of using that lowercase I, which I kind of find a little cumbersome, I just went ahead and used an uppercase I for each of my currents. So you see that through R1, R2, and then R3. And the other thing that we assumed but we didn't explicitly talk about is our current. Our current in each part of our single series loop will be the same, right? This is our charge flow rate. And so our charge flow at part A is the same as our charge flow at part B here, with any part around our loop. So in accordance with Ohm's law, we just simply rewrote the potential difference or the voltage drop across R1, R2, and R3 as the current times the resistance. Notice that I left this term off right here. We do need to deal with that. And so how we're going to deal with that is we are going to use something called an equivalent resistance. And some of you may have used this before. We did this with capacitors. So for our total circuit, so think of this as the EMF for the whole circuit, right? This is our EMF for the whole circuit. We can rewrite that as our current times the resistance for the whole circuit. Now, you could either write here EQ, equivalent, or you could write S for series. I'm going to write S for series right now, just because we have a simple series circuit. All right, so looking at that, you'll notice that the letter I, or the current, appears in each term, and we know that that non-zero current can be divided out, and so we can go ahead and cancel that out from our equation, and then we can simply rewrite, and we rewrite this as our resistance in series is equal to, I'm just going to move my R1, 2, and 3 over to the right-hand side of my equation, R1 plus R2 plus R3. And I think it's pretty easy to extrapolate if we had 4, 5, 6, 7, 8, 10, 20 resistors, that our resistances in series would simply just add together. And so I'd like you to take a moment, and I'd like you to find this equation on your equation sheets right now. So now that we see that our resistances in series all just simply add together, we're going to look at Kirchhoff's junction rule. So Kirchhoff's junction rule is a conservation of charge application. And essentially what it says is the current that goes into a junction has to be the current that's leaving a junction. So you can think of that almost like the number of cars that go in an intersection are the number of cars that go out of an intersection. No, we're not talking about roundabouts here. We're talking about just traditional intersections. And so what this looks like is whatever goes into a junction must go out. We write it, and we want to label the currents as current 1, current 2, current 3. So let's go ahead and identify that for this next setup. Okay, so we have a considerably more complex circuit with 4 resistors and a couple of different loops. What I'd like you to do right now is let's just take a moment and label each of the currents through each of the resistors. You're going to label them I1, 2, 3, or 4, depending on what resistance they go to. So take a moment, I want you to pause the video, and I want you to label, draw this circuit diagram, and then I want you to label your resistances, or excuse me, I want you to label your currents through each of those resistors. All right, so if we label I1, I2, and I3, and let's go ahead and put directions on here. So our charge flow will be to the right here on I1, and then hopefully I think I3 will also be to the right. I2 will be down in this case, since the EMF is pushing the charge in a generally clockwise direction. Now the current that's going through the resistor 4 right here. We could label I4, but if we look very carefully at this, I think that we would see that the current that goes through R1 up here also has to go through R4, right? Because if we go from R4 in our circuit up to R1, notice there's no branching, there's no separation, there's no deviation, there's no junctions. And so the current that goes through R4 also has to go through R1. And so we're going to go ahead and just call that for simplicity. And that's one of the things that when you get more comfortable with using these rules, you're going to see that the currents can be simplified a little bit. So we're going to call this one I1 as well, even though it's going through resistor 4. Okay, so now what we want to do is pick a junction, and you may choose either junction, choose junction B or junction A. So here's junction B and junction A. And what I'd like you to do is I'd like you to write an equation that represents the currents going into and out of the circuit as being equal to each other. So into is going to equal out of. Take a moment and do that. Okay, so we have our junction rules written out. I want you to notice a couple of things about point B. Notice that those directions, those arrows that you drew on your circuit diagram are going to help you figure out what's going into the junction and what's leaving the junction. So the current through R1 is traveling this way. That's clearly into the junction at point B. And then I2 leaves that junction, and then I3 leaves that junction as well, which is why it's all on one side of the equation. If you take a look then at C, you're going to see something similar. We've got I2 and I3 coming into the junction, and then I1 or I4 going out of the junction. Now, notice that these two equations are not independent of each other. They're essentially the same thing. And so using a junction rule, typically you only use the junction rule in solving a circuit diagram once, maybe twice at the most. You're not doing it over and over and over again. But again, we're going to see more of those examples in a little bit. All right, so then what we're going to do is we are going to look at the consequence of the junction rule. So we have a simple parallel circuit right here that you are looking at. So we have the EMF source, and then we have 3 resistances, each with the currents labeled through them. And what I would like you to do is I would like you to add up all of those currents. So you can choose whichever junction you want. Let's do this junction right here. So I'd like you to go ahead and write your junction rule for this junction right here. So take a moment, write that junction rule for that point right there. Okay, so we have looked at the currents that go through the battery. So when we say I total, looking at the current that goes all the way through the battery, that's this guy right here, right? So this is the current that's going through that battery. Now at this junction, we've got 2 things happening. We've got the current through I1, and then we also have the current here that goes through I2, or R2 and R3. And so when we add each of those up, we're going to end up with our total current. So I total is going into this junction right here, and then we have I1, 2, and 3 leaving that junction. Now, just as before, when we used our Ohm's law to rewrite this equation, we're going to do that again. And one thing that we need to recognize is the potential difference across each of our resistors. So when we studied our capacitors, we acknowledged, or we understood, that the potential difference across each of these components, whether they're capacitors or resistors in parallel, will be identical to each other. And so what that really tells us is that the voltage drop across the R1, R2, and R3 are all equivalent to that battery. So if we rewrite this statement in terms of potential and resistances, we get something that looks like this. Just kidding. There we go. Sorry about that. So just as before, we'll notice that those potentials, since they are the same across R1, 2, and 3, they are going to cancel out. And when they cancel out, we see that we are left with 1 over my resistance. Now notice this here, I've changed to, instead of total, I've changed that to a P. So that P there just means parallel. And we can rewrite each of those. Since those potentials drop out, we are left with our resistance in parallel as being 1 over resistance in parallel is equal to the sum of the inverse of each of those resistances. And then notice over here how that circuit's been redrawn, similarly to what we did with capacitors, right? Redrawing those circuits can be very helpful. At this time, if you have not yet downloaded that circuits practice worksheet, I would suggest downloading that practice worksheet. We're going to do an example from that, and then that's your next assignment. That's the problem that I want you to solve. And I will post the key to that tomorrow. So what I'd like you to do is, if you haven't already gotten that, get that worksheet printed or at least pulled up so that you can do that work on a piece of paper. And we're going to start with the 5th one on the front side. We don't exactly have them numbered, but they're the 5th one, and it's going to look like this. I'm going to zoom out a little bit so that we can see more of my screen at one time. So I have my VIR table set up, which is super helpful, right? V is equal to I times R. That makes things nice and easy. And I have my resistances there of R1, R2, and R3. And we have a fairly simple circuit listed there. So take a minute, and I want you to get as far as you can on solving this problem. What do you want to zero in on? What do we want to know? What are we given, right? What are we given? It is my understanding that we are also given a couple other pieces of information. I believe that this is a 6 ohm resistor, that R3 is a 4 ohm resistor, and our R4 is a 15 ohm resistor. Okay, so at this time, pause the video. I want you to solve that as far down as you can, and then I'll pick it up, and then you can either skip ahead to the end of the video and be like, boom, I got it right, or you can follow along with me as we set that up together, or that we solve it together. So I'll give you a moment to think through that. My first step is zeroing in on R2 and R3. I note they are in series. We know resistors in series and add together, so I can replace R1 and R2 with a 10 ohm resistor. I redraw because it helps me think through the problem. I now have a 10 ohm and a 15 ohm resistor in parallel with each other, and so then I use that rule, which is the inverse, right? So the inverse of 10 plus the inverse of 15, and then take the inverse of that. And once you get that, we will see that the total resistance for the entire circuit, again, I just redrew to make that simple, was 6 ohms. So I'm going to go ahead and write that in here as 6 ohms. Now, some of you might be going, hey, wait, what's that? Why is that the same as R1? That's just a coincidence. There isn't anything magical about that. It was just a numerical coincidence. Okay. And so then we take a little bit closer look at our circuit, and I notice that R1 and R2 share the 12 volt potential difference. So if I think about the red, the positive terminal of my battery being the high potential, I'm going to color that in red. That's going to represent my high potential. And then my low potential, or my ground, I'm going to color in blue. Notice my wires have all the same potential. There's no drop across there. So I noticed that my R3 here has the same pressure difference or voltage drop as my battery does. So I'm going to fill that in. I'm going to say, hey, I know that that is also going to have a potential difference of 12 volts. And then once you have two, obviously you can always find the third. So take a moment and calculate that out for us. So we would take, excuse me, our 12 divided by our 15, and we would get 0.8 amps. All right. Now, that is we would call that the loop rule. If you wanted to be very specific about that loop rule, if we took at, and you can look at this in two different ways. If I took this very outside loop, so I'm going to take this loop here, and let's say I start right here, okay, and I transverse that loop clockwise. So I have my 12 volts here, right? And that's going to be a plus 12 volts, travel around the loop. There's no other voltage sources. And so then this is going to have to be minus 12 volts in order to get back to 0, right? So this also has to have another way to show that that voltage across R3 has to also be 12 volts. Okay, so now what we need to do is we need to use our junction rule at one of our junctions, and it does not matter which one you use it for. You can pick which junction you want to use it for. So let's do this junction right here. Why not? We'll do that junction. So we've got the current that goes through I3, right? We also have the current that goes through I1 and I2. Now, notice that's not I1 plus I2, it's I1 and 2. They are the same, right? Because those two are in series with each other. So if we take a look at, let's clean this up a little bit so we have a little bit less stuff to look at. If we look at this junction right here, our current that's going through our battery is also going into that junction. So we would have I total is going to have to be equal to, which would be 2 amps, would have to be equal to the current that's going through R3, which is 0.8 amps, plus the current that's going through R1 and R2. And so the current that's going through both R1 and R2 would just be the difference between those. So the current for both R1 and R2 would be 1.2 amps. Now we're home free. And then the table will give us some consistency checks that we can look at as well. So when we want to find our potential difference across R1 and R2, we simply multiply those together. And when we do that, we will get 7.2 volts and 4.8 volts. And if you add these two together, which again, this is going to be our loop rule, if we add the potential difference across R1 and R2, you're going to notice that they add up to our battery voltage. So these two are going to add up to that 12 volts. All right, so now what I'd like you to do is I'd like you to do that practice worksheet. I'd like you to try the rest of those. I will be posting keys to those tomorrow. Have a wonderful day and best of luck to you.